All right, so we've been talking all about waves, but now we're embarking on a new topic, optics, which admittedly is only kind of a new topic because light, as we'll see, is kind of a wave. The wave-particle behavior of light is quite interesting and undeniable given the results of some key experiments. How can light be both a particle and a wave? Well, perhaps it's neither, but demonstrates the behavior of each depending on the situation. Perhaps it's some yet-to-be-discovered something which behaves consistent with the properties of that something at all times. We've just yet to fathom what that something is. What we do know is what I'm going to encourage you to accept is that sometimes light behaves like a particle, and sometimes light behaves like a wave. So let's learn about those sometimes's. By the way, the complete answer is given by quantum electrodynamics, a field of study well beyond the scope of this course, but the short answer for us can be summed up by the following. The propagation of light, how it travels, is best described by a wave model, while emission and absorption of light is best described by a particle model. Even simpler, and I'll caution you that oversimplifications can be dangerous, light seems to travel as a wave, but start and end its journey as a particle. So the source of all electromagnetic radiation, or light, as you know from your E&M course, is a charged particle accelerating. Anytime a charged particle, like an electron, accelerates, light is produced. This event can occur due to thermal activity, as in thermal radiation, or in a stimulated fashion, like with lasers. But generally, this occurs whenever atoms go from a higher to a lower energy state. The difference in energy between the higher and lower states exits the system in the form of a photon, or a single quantum of light. Well, regardless of the choice in wave or particle model, and regardless of the source, light always travels in a vacuum at the same speed, and that is the speed of light, c, in a vacuum, which is 2.997924 to the best that we know now, times 10 to the 8th meters per second. Oftentimes you'll see this abbreviated to just, or approximated, 3 times 10 to the 8th meters per second, because it's very close to that. When we're talking about light as a wave, the concept of a wavefront is useful. A wavefront is the leading edge of a wave, where all adjacent points along this leading edge are in the same phase or same part of their cycle. So if we're talking about sinusoidal wave representing a photon, this, let's say, is our reference point in the cycle. These would all be wavefronts here. Didn't draw it such that I could provide many more examples, but it's at the same point in its cycle here. So these would be wavefronts, and they would continue on. On the other side of our consideration of light, when we're thinking about light as a particle, the concept of a ray is useful. Rays are straight lines along which light travels. A ray is perpendicular to the wavefront. So if we represent a ray like this, and it has a direction, I could have done an arrow. There we go, there. Then the wavefronts would be perpendicular to that, say, wow, like this. So periodic wavefronts that are perpendicular to the direction of travel of the ray. The branch of physics that deals with light as rays is called geometric optics. I'll say rays. And the branch of physics that deals with light as wavefronts is called physical optics. Wavefronts. So this lecture and the next we'll talk about geometric optics. Then lectures 6 and 7 we'll talk about physical optics.